Hello everyone and welcome to the fourth lecture of the logic part of Comp 0003. Today's lecture is going to be on Boolean algebra, which can be seen as a version of propositional logic dealing only with and, or, and not, and written down in a different notation. It's also quite similar to some traditional algebra using addition and multiplication, in a quite similar way to the way we're all familiar from high school. To be honest, I find Boolean algebra quite dull, which is why we're only going to devote one lecture to it. It's fairly straightforward. I mean, if you understand propositional logic, and hopefully by now you do, then I would say picking up Boolean algebra should be pretty easy as well. So let's try and get through it nice and quickly. I think we won't come back to me again today, so we'll just we'll go straight to the slides and I'll see you all at the end. Okay, so Boolean algebra is named after the chap who invented it, who's this guy with the mutton chops here, George Boole, who lived in the early to mid 19th century. He introduced his Boolean algebra in a work called The Laws of Thought in 1854. Now that's actually a bit before propositional logic was written down in the way that we've seen it written down in the last couple of lectures, but it is essentially propositional logic. It can be viewed as one of the first works in propositional logic, but where everything is kind of written down in algebraic terms rather than as sort of formulas in the form that we've seen them before. So let's go and have a look at the definition of a Boolean algebra. So a Boolean algebra is a tuple. By the way, a tuple is really just a list of things. So a tuple, B, 0, 1, plus, and minus, where B is a non-empty set. So it could be a set of anything, by the way, but it has to have certain kind of other properties. But what objects are in the set doesn't matter that much. The set has got to contain two elements, which we're calling 0 and 1. So 0 should be thought of as false and 1 as true. So they have to be two objects in the set B. And then plus has to be a so-called binary function on B. So plus is a function. It takes in two elements in B and returns another element in B. Just like addition on the natural numbers, for example. But here you should really think of plus as being a lot like the logical connective OR. Next, we should also have a unary function on B, which is called minus, so it has type B arrow B. And I think it should be thought of as being the same as negation in propositional logic. I'm also going to introduce a couple of abbreviations. First of all, this A with a bar over it, bar A for minus A, just because it takes a little bit less space on the page, so that's quite a common way of writing that down. And A dot B for minus A plus minus B. Now remember that if we're thinking of plus as disjunction and minus as being negation, then minus A plus minus B is really not A or not B. And by the De Morgan laws, that is exactly the same thing as A and B. So A dot B is really the same thing as A and B. So dot is kind of an and in this setup. A Boolean, that's not all though. The 0, 1, plus, minus have also got to obey certain kind of axioms, which I think we'll go and look at, right now. So first of all, we're going to have a whole bunch of axioms for plus. First of all, we're going to insist that the plus should be an associative operation. So A plus B plus C is equal to A plus B plus C. That's the associativity law. And remember that it's also true of OR in propositional logic. Similarly for commutativity, so the order in which you write down terms doesn't matter in a sum. A plus B is equal to B plus A. Again, that's true of disjunction as well. Next we have so-called idempotency. That's what this law is called. A plus A is equal to A. Now, of course, this isn't really true in kind of standard algebra, but it is true of OR. Again, A or A is just the same thing as A itself. Next we have the so-called unit law for the interaction with 0. 0 plus a is equal to a. Now that's true in standard algebra, but it's also true if you read 0 as being false, or an unsatisfiable formula, and plus is or. Because if we have false or a, well, I mean, since false is impossible, that's exactly the same thing as a itself. Next we have some axioms for minus. First of all, minus minus a is equal to a. Now, we know that's true because we know that not a is the same thing as a in propositional logic. We also have a plus minus a is equal to 1. So here, well, I mean, this is actually, this is really just the law of excluded middle, but written down in algebraic form. A or not a is equal to 1, which is true, remember. Next, we have the connection between 0 and 1. Remember that 1 and 0 are true and false, respectively. So the axiom says that minus 1 is equal to 0. If you negate true, you get false. That can be seen as saying that if you take the negation of a valid formula, for example, any true formula, then you get a false formula. And finally, we have the so-called distribution law. A dot b plus c equals a dot b plus a dot c. Now this is true if you read dot as being and plus as being or, because we have a and b or c is exactly the same thing as a and b or a and c. And we saw that before. So all of these axioms of Boolean algebra are just laws of classical propositional logic, but written down in an algebraic way. So a Boolean algebra is any set, big B, together with a suitable choice of 0, 1, plus, and minus, such that all of these axioms are satisfied. So here's our first example of a Boolean algebra, and it's pretty much the simplest one you could think of. This Boolean algebra just contains two elements, 0 and 1. So my set B is just a set 0 and 1. And then I've taken the 0 of the algebra is 0, the 1 of the algebra is 1. And plus and minus are defined by the following tables. So plus, here's a table for plus. So 0 plus 0 is equal to 0. And in all other cases, a plus b is equal to 1. So a plus b is equal to 1 if at least one of its arguments is 1 as well. You can see that that is the same thing as or in propositional logic. It's just a slightly different way of writing down the truth table. And minus has an even simpler table. It just sends 0 to 1 and 1 to 0, which is exactly what you'd expect for negation in propositional logic as well. So this is a Boolean algebra. You could either check all the axioms individually, or you could just notice that plus is here, or, and minus is negation, and just notice that all the axioms are true in propositional logic. So so just here I've written down explicitly that plus corresponds to disjunction, minus to negation, and dot, which I haven't given a truth table for here, or an algebraic table, but if I did, then it would be remember that a dot b is equal to minus a plus minus b, and that would kind of correspond to conjunction. What would happen is that a plus b would turn out to be 1 if a and b are both 1 and 0 otherwise. And here's the second example of a Boolean algebra. So first of all, take any non-empty set X and define its power set to be the set of all subsets of X. So power X is so-called the power set of X, and it's equal by definition to the set of all sets Y such that Y is a subset of X. Then, if I take this guy here, then this thing is a Boolean algebra. Let me just talk you through what each of those things are. So the 0 of the algebra is the empty set. The 1 of the algebra is just the set X itself. And remember that these are both subsets of X for sure. So they are in particular, they're members of the power set of x, so that's okay. And then for my plus, I'm going to take the operation cup for the set union. So a plus b, remembering that a and b are both subsets of x, is the union of a and b. And then as for the minus of the algebra, I'm going to take, so minus a is going to be x minus a, so set complement. And if a is a subset of x, then so is x minus a. So that is that's an operation on power set of x as well. And you can check that this definition also satisfies all the axioms of Boolean algebra. And this is kind of special Boolean algebra, which is called a Boolean set algebra. And they're kind of special in the following way, that really there's a theorem by Stone in 1936 that every Boolean algebra is isomorphic to a Boolean set algebra. So while I won't go into the definition of an isomorphism, it basically means it is essentially the same thing as. So every Boolean algebra somehow can be seen as a Boolean set algebra. So one useful application of Boolean algebra comes from its connection to hardware, and in particular electronic circuits. Of course, a circuit takes in a number of inputs, which either there will be a current going through them or not, so either 0 or 1, depending on whether there's current or not. And depending on the inputs, they will return some kind of an output, which is constructed using gates. So here's a NOT gate, and please excuse my fairly rudimentary LaTeX drawing skills here. A NOT gate takes in a single input, x, and returns as output not x, so it negates the output. So if it takes in a 0, it returns 1, and vice versa. Here's an OR gate that takes in two inputs and returns and has as output 1 if at least one of the inputs is 1 or live. So it takes in x and y and returns x plus y, in other words. And here we have an AND gate, which takes in two inputs, x and y, and returns x dot y. In other words, it returns 1 if both of its inputs are 1. And you can also, of course, there are other kind of gates as well, like NAND gates, which are basically made by combining NOT gates and AND gates and so on. And I think it should be fairly obvious that on the one hand, if I were to give you a Boolean term, then you could construct a circuit that corresponds to it, a circuit that, if you like, implements that Boolean term. And conversely, if I was to give you a circuit built out of these gates, then you could write down a Boolean term that corresponds to it. So that's quite useful, just as a kind of succinct way of describing electronic circuits. Next, let's look at some De Morgan laws. So we have two of them here. We have minus a plus b is equal to minus a dot minus b. And we have minus a dot b is equal to minus a plus minus b. Now, if you remember that minus is not, plus is or, and dot is and, then these are true laws in propositional logic. They're the De Morgan laws that we talked about before. So not a or b is equal to not a and not b. And not a and b is the same thing as either not a or not b. And these are very easy to derive from the axioms. If we do the first one here, minus a plus b is equal to, we can just double negate both a and b, so we get that it's equal to minus minus a plus minus minus b. And then immediately that is equal to minus a dot minus b by definition. Because remember that a dot b is minus minus a plus, minus minus a plus minus b. So if you put in minus a for a and minus b for b, then you get exactly this term here. So that's equal by definition. Next, for the other one, we will let's take minus a dot b, and that's equal to minus a plus minus b. That's just by putting in this term here for a dot b. That's just by the definition of dot. And then by double negating that, or removing the double negation, then we get that it's equal to minus a plus minus b. And we're done. Easy. Okay, so now we're going to do a couple more derivations. Our first one is going to be a dot minus a equals 0. Now that's just an algebraic statement of the law of non-contradiction. A and not a is false. And we'll go into it in the following way. The complement law says, like our law of excluded middle, a or not a is true. So by the same token, not a or not a is also true. That's just by taking the case where a is the statement not a. So an instance of our complement axiom is minus a plus minus a equals 1. And then if I apply minus to both sides, I get minus a plus minus a is equal to minus 1. And minus 1 is equal to 0 by the 0 and 1 axiom. And then if I just look at this left-hand guy here, I can see that by definition, this is exactly equal to a dot minus a. Because remember that a dot b is minus a plus minus b. So if I take minus a for b in that equation, I get exactly this guy here. So that gives us a dot minus a equals 0, which is what we wanted. Next example, a dot 1 equals a. Now, in propositional logic terms, that just says a and true is equivalent to just a by itself. So this example I think we'll do just by starting at the left-hand side and going all the way over to the right-hand side using our laws. So let's do it as follows. A dot 1 is equal to a dot minus a plus a. That because our complement law says that a plus minus a is equal to 1. And also minus a plus a is equal to 1 by commutativity. Don't know why I've written it this way around. I don't think it matters. So that's just by rewriting 1 according to the complement law. Next, we'll apply our distribution law. Remember that the distribution law says a dot b plus c is equal to a dot b plus a dot c. So just by taking minus a for b and a for c in that law, I get a dot minus a plus a dot a. And then our first item above, the thing we proved just before, is exactly that a dot minus a is equal to 0. So we can rewrite the left-hand term as 0. And as for the right-hand term, well, we have a dot, so we can just rewrite it according to the definition of dot, which means I'll get exactly minus a plus minus a. And I can then apply my law of idempotency to say, well, actually, minus a plus minus a is equal to just minus a. And then I have, of course, a double minus here, so I can eliminate that to get just 0 plus a. And then finally, I can use my unit law axiom to eliminate the 0. 0 plus a equals a. So, fairly straightforward. As a little exercise, you might like to prove some more interesting things. You could prove a dot 0 equals 0. In other words, a and false is false. And the law a plus 1 equals 1. In other words, a or true is true. So here's a useful theorem of Boolean algebra called the duality theorem. For any true equation in Boolean algebra, let's say a equals b, then we have that a star equals b star is also a true equation. And here a star and b star are obtained from a and b by swapping plus and dot and swapping 0 and 1. So you write plus for every dot and dot for every plus, and the same for 0 and 1. Why should this be true? Well, actually, if you go back to the axioms of Boolean algebra, and you just do that swapping operation, then you can observe that you actually end up with a set of dual axioms which are also true in propositional logic, and you can check that they hold in Boolean algebra. So, for example, here's the standard distribution law, which is an axiom of Boolean algebra. A dot b plus c equals a dot b plus a dot c. By the way, I should just mention here that In Boolean algebra, we usually think of dot as binding tighter or having higher precedence than plus. So a dot b plus a dot c is written is all, even without the brackets, is kind of read as though a dot b in brackets plus a dot c in brackets, and not some other way around. And that's also quite similar to standard algebra, where you also think of multiplication binding tighter than addition. So if we apply our duality principle, then we're going to get a dual distribution law, which is a plus b dot c equals a plus b dot a plus c. Now, that's true in propositional logic, because we have the distribution principle that a or b and c is equal to a or b and a or c. So that's true in propositional logic. It's also true in Boolean algebra, and we can check that. Just as an exercise, we could try writing down and perhaps proving some other identities that follow by duality. So let's check that this dual distribution law does hold. So I've written it here at the top again. And I'm going to approach it this time by working from the right-hand side and working my way over to obtain the left-hand side. It's just a bit easier to do it that way in this case. So let's start with the right-hand side. And we're going to, essentially multiply out the brackets as we would in standard algebra. I'll do it in 2 steps. We have that a plus b dot a plus c is equal to a plus b dot a plus b dot c. So that's kind of some of the brackets multiplied out, and we can multiply out the rest as well to get a dot a plus b dot a from the first term, and plus a dot c plus b dot c from the second term. So now I can write a dot a as a dot 1. Why? Well, we have the equations a dot a equals a. Now, I don't know if I actually proved that, but it's definitely true. And it's quite easy to prove. Remember that if you were to take the definition of a dot a, it would be minus a plus minus a, just by the definition of dot. And then using the idempotency law, you would get that is equal to just minus a, because minus a plus minus a is equal to minus a by idempotency. And then by double negating, you get that minus a is just a, of course. And we also have the equation a is equal to a dot 1. We proved that a couple of slides back. So here I've just replaced a dot a by a dot 1, which is a true statement. And now I will factor out again. I see that I've made a little mistake on the slide here. What I meant to do was I wanted to factor out a from these first 3 terms, and so I should have deleted this one, but I didn't. So ignore that one. But this is equal to a dot 1 plus b plus c. That's really by applying the distribution law twice, but I kind of condensed those steps. Plus, just ignore that. Plus b dot c, which we didn't do anything with. So, because we have 1 plus b plus c is equal to 1, that I think that was an exercise a couple of slides back, that 1 plus a equals 1 for any a. So in particular, 1 plus b plus c is equal to 1. So this term just becomes a dot 1 and plus b dot c. And then, of course, we have a dot 1 is equal to a, so that gives us a plus b dot c. And we're done. The last thing that I wanted to talk about related to Boolean algebra is the sum of product form of Boolean terms. So a sum of products in Boolean algebra is essentially the same thing as a disjunctive normal form formula in propositional logic. So remember that in propositional logic, we can convert any arbitrary propositional formula to one in disjunctive normal form, or DNF, where a disjunctive normal form formula is on the outside a big disjunction of things, and the things are conjunctive clauses, which are conjunctions of literals, where literals are either proposition letters or their negation. In the same way, we can write every Boolean algebra term as a sum of products. So on the outside, it's a big sum of things, and the things are products, dot products of either individual variables, you know, A, B, C, or their negations, bar A or minus B, minus C. So again, we're not allowing ourselves to have any negations outside of sums, outside of products, and never more than one applied to a variable. So if we have constructed the truth table of a term, which we can do in the kind of obvious way, then again we can read off a sum of products just directly from the truth table, in the same way that we read a disjunctive normal form formula off from the truth table of the formula. Or again, like in propositional logic, we can use equations or equivalences in propositional logic and equational laws here. So the way you would do it is exactly the same method as in propositional logic, except we don't even have to worry about getting rid of implications because there aren't any. So first of all, we use De Morgan laws, so we can replace minus a plus b by minus a dot minus b. That's a De Morgan law. And similarly, we can replace minus a dot b by minus a plus minus b. And any double negations, minus a by a. So that's a way of kind of driving all the negations down to as low down in the formula as we can. So if you see double minuses can be eliminated immediately, and if you have a minus that's outside a plus or a dot, which is not allowed in a sum of products, then you can just use these De Morgan laws to kind of push it in a bit further. And finally, if you have a dot outside of a plus, which is not allowed in a sum of products because a sum of products has to be a sum on the outside and the sum has to be a sum of products. So whenever we have a dot b plus c, then we can also get a dot b plus a dot c. That's just by the distribution law. By the way, you could also write every Boolean term, instead of a sum of products, you could also write it as a product of sums, which would be more or less the same kind of operation, except that you would use the dual distribution law to push sums inside of products. So you use a plus b dot c is equal to a plus b dot a plus c. So this same method would get you either to a sum of products or a product of sums, depending on what you want. Of course, a product of sums is like a CNF, conjunctive normal form, in propositional logic. And I think that's pretty much all there is, or at least all I want really to say about Boolean algebra. And I think it's time for some concluding remarks. So, I mean, propositional logic and Boolean algebra, I think we've seen that they really are just sort of two ways of looking at the same basic thing. You're still examining the structure of connectives somehow, but it's not very expressive. Yes, we can connect propositions and negate them and that kind of thing, but we don't have any way of kind of getting inside propositions other than kind of logical connectives. So I can't look at a property that says, my car is blue or something like that. We don't have any way of quantifying anything either. And that means that, for example, if we look at this kind of Aristotelian syllogism that we saw in the first lecture, all men are mortal, Socrates is a man, therefore Socrates is mortal. I mean, there's no real way of formalizing that either in Boolean algebra or in propositional logic in a way that actually gets to the essence of this argument. We don't have any way of quantifying or saying that a particular object has a particular property or anything like that. So really, we would, in propositional logic, these three things, these three lines they're all propositions, but we would have to view them as kind of just three propositions P, Q, and R, and they wouldn't really be connected in any kind of in any real way. But of course they are connected, And the answer is really that we have to go to a more expressive logic where we can capture properties of objects and quantified statements. So for that, we're going to need to move to first order logic, and that's going to be the subject of the next few lectures. Okay, that's the end of the lecture, and topic completed. So well done for that. Next lecture, we're going to start looking at so-called first order logic, which I think is far more interesting than either propositional logic or Boolean algebra. So I'm looking forward to that, and I hope you are too. So well done, and I'll see you next time.